Compare and contrast classical free and quantum free electron theory. Classical free electron theory. Free electron concept. All metal atoms consist of valence electrons and they are responsible for physical properties of metals such as electrical and thermal conductivities, thermoelectricity, thermionic and photoelectric effect, etc. According to Jude Lawrence theory, when a large number of atoms arranged in three-dimensional lattice points to form a metal, the boundaries of the neighboring atoms slightly over with each other as shown in the figure. Due to this overlapping, the valence electrons of all the atoms are free to move within the metal lattice. Assumptions of classical free electron theory. All metals contain large number of free electrons which move freely through the positive ionic core of the metals. Since these free electrons causes conduction in metal under the application of electrical field, they are called as conduction electrons. The free electrons are treated as equivalent to gas molecules. The law of classical kinetic theory of gases can be applied to them. Therefore, these electrons have mean free path, mean collision time, the average speed. In the absence of the electrical field, the kinetic energy associated with an electron at a temperature T is given by half mv/Th, where V is the thermal velocity of the electron and which is equal to root mean square velocity c. Since the motion of the electrons is random, the net current is zero in the absence electric field, but when an electric field is applied, current is produced due to the drift velocity of the electrons. Drift velocity. It is the average velocity acquired by the electrons in a direction opposite to the direction of the applied electric field. Mean free path. The average distance traveled by the conduction electrons between two successive collision with lattice ions is known as mean free path. Mean collision time. It is the average time that elapses between two successive collision of an electron with lattice points. Relaxation time. The relaxation time is a measure of the rate at which relaxation takes place. Success of classical free electron theory. The successes of this theory are: it verifies Ohm's law, it derives Wiedemann-Fries, it explains electrical and thermal conductivity of metal, it explains optical properties of metal. Drawbacks of classical free electron theory. Specific heat. The specific heat of a gas at constant volume is given by Cv equal to 1 by 2R, where R is the universal gas constant. But experimentally, it was observed that the specific heat of a metal by its conduction electron is given by Cv equal to 10 power minus 2 RT. Mean free path. According to classical free electron theory, the mean free path gamma equal to C vector dou, where c vector is the root mean square velocity and dou is the relaxation time of conduction electrons. We also know that by substituting the values of E, M, N and P for a metal, dou can be calculated. But the experimental value of dou is found to be 0.285 nm, which is 10 times less than the value obtained from classical free electron theory. Hence, classical free electron theory fails to explain. The third one is temperature dependence of electrical conductivity. And the fourth one is dependence of electrical conductivity and electrons concentration. Quantum free electron theory. To overcome the drawbacks of classical free electron theory, Sommer proposed quantum free electron theory. He treated electron as a quantum particle. He retains the vital features of classical free electron theory and included the Pauli's exclusion principle and Fermi-Dirac statistics. The following are the assumptions of quantum free electron theory. The free electrons in a metal can have only discrete energy values, thus the energies are quantized. The electrons obey Pauli's exclusion principle, which states that there cannot be more than two electrons in any energy level. The distribution of electrons in various energy levels obey the Fermi-Dirac quantum statistics. Free electrons have the same potential energy everywhere within the metal because the potential due to ionic cores is uniform throughout the metal. Fermi-Dirac statistics. There are three statistics are there in Fermi-Dirac statistics. First one is Maxwell Boltzmann statistics. Second one is Bose-Einstein statistics. Third one is Fermi-Dirac statistics. Fermi level, Fermi energy, and Fermi factor. A metal containing n atoms, there will be n number of energy levels in each band. According to Pauli's exclusion principle, each energy level can accommodate a maximum of two electrons, one with spin up and the other with spin down. At absolute zero temperature, two electrons with opposite spins will occupy the lowest available energy level. The next two electrons with opposite spins will occupy the next energy level and so on. Thus, the most energy level occupied by electrons at absolute zero temperature is called Fermi energy level. The energy corresponding to that energy level is called Fermi energy. Merits of quantum free electron theory. The quantum free electron theory solves the flaws of the classical free electron theory, which are discussed below. Specific heat of free electrons, temperature dependence of resistivity or conductivity in metals, dependence of electrical conductivity on electron concentration. Similarities between classical and quantum free electron theory. The following assumptions apply to both the theories. The valence electron are treated as though they constitute as ideal gas. The valence electron can move freely throughout the body of the solid. The mutual repulsion between the electrons and the force of attraction between the electrons and ions are considered insignificant. Difference between classical and quantum free electron theory. Classical free electron theory. The energy levels of free electron are continuous. Quantum free electron theory. The energy values of the free electrons are discontinuous, that is, the energy level are discrete. The free electrons may possess same energy. Free electrons obey Pauli's exclusion principle, that is, no two electrons can have same energy. The distribution of electrons in various energy levels obeys the Maxwell-Boltzmann statistics. The distribution of electrons in various energy levels obey the Fermi-Dirac statistics. Thank you.